Dear students, welcome to the lab 11 of CS351 lab, Artificial Intelligence lab, where we will be continuing with unsupervised learning and talking specifically about the K-means clustering. The contents of this lab are designed by me, Dr. Raja Hashim Ali, and I'm currently teaching this course at Ghulam Isa Khan Institute of Engineering, Science and Technology. So from this lab, we wish to learn the introduction and implementation of K-means clustering. We want to understand and apply K-means clustering to machine learning problems and as a simple data compression technique in images. We want to evaluate when K-means clustering is useful and when it is faulty. Learning outcomes from this lab are: after successful completion of this lab, the student will be able to explain the basics of unsupervised learning, apply and implement solutions for clustering problems using K-means clustering. Instructions are that you need to have a computer where you can sit in front of and use Python. So in this lab we'll cover K-means clustering, which is considered as one of the most used clustering algorithms due to its simplicity. The K-means algorithm is an iterative algorithm that tries to partition the dataset into K predefined distinct non-overlapping subgroups or clusters where each data point belongs to only one group. It tries to make the interclustered data points as similar as possible while also keeping the clusters as different or far as possible. It assigns data points to a cluster such that the sum of the squared distance between the data points and the cluster's centroid, or the arithmetic mean of all the data points that belong to that cluster, is at the minimum. The less variation we have within the clusters, the more homogeneous or similar the data points are within the same cluster. So the algorithm, the way K-means algorithm works is as follows. We specify the number of clusters K, initialize centroids by first shuffling the dataset and then randomly selecting K data points for the centroids without replacement. Keep iterating until there is no change in the centroids, that is, assignment of data points to cluster isn't changing. We compute the sum of the squared distance between data points and all centroids. We assign each data point to the closest cluster or centroid, and we compute the centroids for the clusters by taking the average of all data points that belong to each cluster. The approach K-means follows to solve the problem is called expectation maximization. The E step is assigning the data points to the closest cluster. The M step is computing the centroid of each cluster. Few things that are to note here is that since clustering algorithms including K-means use distance-based measurements to determine the similarity between data points, it is recommended to standardize the data to have a mean of 0 and a standard normal deviation of 1. Since almost always the features in any dataset would have different units of measurement, such as age versus income. Given the K-means iterative nature and the random initialization of centroids at the start of the algorithm, different initializations may lead to different clusters, since K-means algorithm may be stuck in a local optimum and may not converge to global optima. Therefore, it is recommended to run the algorithm using different initializations of the centroids and pick the results of the run that yield the lower sum of squared distance. Assignment of examples isn't changing in the same thing as no change in within cluster variation. The K-means algorithm is very popular and used in a variety of applications such as market segmentation, document clustering, image segmentation and image compression, etc. The goal usually when we undergo a cluster analysis is either to get a meaningful intuition of the structure of the data we are dealing with, or the cluster then predict where different models will be built for different subgroups if we believe that there is a wide variation in the behaviors of different subgroups. As example of that is clustering patients into different subgroups and build a model for each subgroup to predict the probability of the risk of having heart attack. In this lecture we will apply clustering on two cases. One is a geyser eruption segmentation 2D dataset and on image compression. When we apply K-means on geyser eruption segmentation, we will first implement the K-means algorithm on 2D dataset and see how it works. The dataset has 272 observations and 2 features. The data covers the waiting time between eruptions and the duration of the eruption for the Old Faithful geyser in Yellowstone National Park, Wyoming, USA. We'll try to find K subgroups within the data points and group them accordingly. Below is a description of the features. Eruption is a float, which is eruption time in minutes, and then you have got waiting in integer, which is basically waiting time to next eruption. So let's plot the data first, and here are the commands that you have to run in matplotlib.pyplot, and these are all commands of Python, and you need to run them in directly. We'll then use this data because it's easy to plot and visually spot the clusters since it's a two-dimensional data set. It's obvious that we have two clusters. Let's standardize the data first and run the KMeans algorithm on the standardized data with k is equal to 2. The above graph shows the scatter plot of the data colored by the cluster they belong to. In this example, we chose k is equal to 2. The symbol static is the centroid of each cluster. We can think of those two clusters as geyser had different kinds of behaviors under different scenarios. Next, we'll show that different initializations of centroids may yield to different results. I'll use 9 different random state to change the initialization of the centroids and plot the results. The title of each plot will be the sum of square distance of each initialization. As a side note, this dataset is considered very easy and converges in less than 10 iterations. Therefore, to see the effect of random initialization on convergence, I am going to go with 3 iterations to illustrate the concept. However, in real world applications, datasets are not at all that clean and nice, as you can see over here. Okay, as the graph above shows that we only ended up with 2 different ways of clustering based on different initializations. We would pick the one with the lowest sum of squared distances. And now we move on to the second problem, which is basically k-means or image compression. In this part, we will implement k-means to compress an image. The image that we will be working on is 396 by 396 by 3. Therefore, for each pixel location, we would have 3 8-bit integers that specify the red, green and blue intensity values. Our goal is to reduce the number of colors to 30 and compress the photo using these 30 colors only. To pick which colors to use, we'll use KMeans algorithm on the image and treat every pixel as a data point. That means reshape the image from height into width into channels to height into width into channel. That is, we would have 396 by 396 data points in 3-dimensional space, which are the intensity of RGB. Doing so will allow us to represent the image using the 30 centroids for each pixel and would significantly reduce the size of the image by a factor of 6. And this means that the next thing that we need to do is to see that the original image was basically 396 by 396 by 24 bits. However, the new compressed image would be just 627984 bits, which is far. The huge difference comes from the fact that we'll be using centroids as a lookup for pixels color, and that would reduce the size of each pixel location to 4-bit instead of 8-bit. From now on, we'll be using the SKlearn implementation of KMeans. Few things to note here are that n_init is the number of times of running the KMeans with different centroids initializations. The result of the best one will be reported. The TOL is the within cluster variation metric used to declare convergence, and the default of init is KMeans++, which is supposed to yield a better result than just random initialization of centroids. And that is the code. You can put it in. You can feed it the original image and see the result of compressed image. You'll see that there's not much of a difference between compressed image and original image. We can see that the comparison between the original image and the compressed one, the compressed image looks close to the original one, which means we are able to retain the majority of the characteristics of the original image. With smaller number of clusters, we would have higher compression rate at the expense of image quality. As a side note, this image compression method is called lossy data compression because we can't reconstruct the original image from the compressed image. The drawbacks of K-means algorithm. The K-means algorithm is good in capturing structure of the data. If clusters have a spherical like shape, it always tries to construct a nice spherical shape around the centroid. That means the minute the clusters have a complicated geometric shape, K-means does a poor job in clustering the data. We'll illustrate 3 cases where K-means will not perform well. First, K-means algorithm doesn't let data points that are far away from each other share the same cluster even though they obviously belong to the same cluster. So here's an example, and here's what you can see. You can put in the code and see. The K-means considers the point B closer to point A than point C since they have non-spherical shape. Therefore, points A and B will be in the same cluster, but point C will be in a different cluster. Note that the single linkage hierarchical clustering method gets this right because it doesn't separate similar points. Second, we'll generate data from multivariate normal distributions with different means and standard deviations. So we would have 3 groups of data where each group was generated from different multivariate normal distribution, different mean and different deviation, standard deviation. One group will have a lot more data points than the other two combined. Next, we'll run K-means on the data with k is equal to 3 and see if it will be able to cluster the data correctly. To make the comparison easier, I'm going to plot first the data colored based on the distribution it came from. Then I'll plot the same data but now colored based on the clusters they have been assigned to. Here's a code and here's a result, and here's what you can see. Looks like K-means couldn't figure out the clusters correctly. Since it tries to minimize the within cluster variation, it gives more weight to bigger clusters than smaller ones. In other words, data points in smaller clusters may be left away from the centroid in order to focus more on the largest clusters. Finally, we'll generate data that have complicated geometric shapes such as moons and circles within each other and test K-means on both of the data sets. Here's the code and here's the result. As expected, K-mean couldn't figure out the correct clusters for both data sets. So finally concluding, K-means clustering is one of the most popular clustering algorithms and usually the first thing practitioners apply when solving clustering tasks to get an idea of the structure of the dataset. The goal of K-means is to group data points into distinct non-overlapping subgroups. It does a very good job when the clusters have a kind of spherical shapes. However, it suffers as the geometric shapes of clusters deviates from the spherical shapes. Moreover, it also doesn't learn the number of clusters from the data and requires it to be predefined. To be a good practitioner, it's good to know the assumptions behind algorithms or methods so that you would have a pretty good idea about the strength and weaknesses of each method. This will help you decide when to use each method and under what circumstances. In this lab, we covered both strengths, weaknesses, and some evaluation methods related to K-means. Below are the takeaways. Scale standardize the data when applying K-means algorithm. K-means gives more weight to the bigger clusters. K-means assumes spherical shapes of clusters with radius equal to the distance between the centroid and the furthest data point and doesn't work well when clusters are in different shapes such as elliptical clusters. If there is overlapping between clusters, K-means doesn't have an intrinsic measure for uncertainty for the examples belonging to the overlapping region in order to determine for which cluster to assign to each data point. K-means may still cluster the data even if it can't be clustered such as data that comes from uniform distribution. Thank you. I'm done.